there is another speaker that is Alessandro Viani from the Department of Mathematics of the University of Genoa, and I will talk about Bayesian model. And in particular, he talks about stable multi-dipole estimation from magnetoelectroencephalography data through the use of hyperprior. Alessandro, okay.
Do you see my screen? Yeah.
Yes, I see.
You also see there. Okay. Thank you very much. Hello, everyone. What I'm talking about today is the resolution of the MEG inverse problem using a full Bayesian approach. And the resolution of the problem will be done with a particular algorithm, a particular Monte Carlo algorithm belonging to the class of sequential Monte Carlo. And the aim here is the make the problem independent from some a priori parameter by the introduction of an hyperprior in the model. And at the end, we will see some numerical results in synthetic data and in synthetic data. At first, we have to focus on the model we used for represent the neural activity. We used the Depolar model, where we have already seen by Carster this morning. And we saw that a dipole is a point source characterized by two quantities. The first one is the position, and it is nothing but an index inside the brain discretization. And then we have the dipole moment, that is a three-dimensional vector that tells us the direction and the intensity of the electric field in the brain, in this in the dipole. And we already saw that the link between what we measure, so the electric or the magnetic field, is linked by the position and the dipole moments by this equation. And we see that the problem is linear in the dipole moments, so in Q, that before at the first talk this morning was called M, and in the positions is not non-linear. But what are the main features of using a Depolar model instead of a distributed one? That is the one that Alexandra used in her research. The main feature of this model is that we can use a small number of active sources inside the brain. But there is, for one win, there is one lose, because here we have to work with an unknown number of sources. And we thought that we want to establish we want to formulate the inverse problem of MEG using a Bayesian approach. So at first we have to focus on what are the data that are the measures made by some sensors outside of the scalp, and then which are the unknown. The unknown are the number of dipoles, because we are using a Depolar model, their position of each dipole, and then we have the moments of each dipole. Then the link for the posterior, that is the in target density. This is the density that we are interested in if we are working in a Bayesian approach, is linked with the prior times the likelihood and by the bias theorem. The prior embodies what we know about the unknown before the measurement. So these are all everything we know about the number of dipoles, their position, and the dipole moments. And then we have the likelihood. The likelihood is the probability of measuring the magnetic or the electric field having fixed some configuration inside the brain. And then we have a normalizing constant that in this particular problem is not interesting. But how can we get an approximation of the posterior distribution? We can use something like Monte Carlo methods. And I would like to focus some more in this, because the focus here is not to get an approximation of only a point or an estimator of the posterior. We would like to estimate the posterior distribution, the posterior density. That is something different from, for example, the maximum of posteriori or maximum likelihood. And so we want to use Monte Carlo methods. The used one, we said at first in the introduction, that is the sequential Monte Carlo samplers. But for talking about and explaining briefly what sequential Monte Carlo samplers are, we have to at first introduce two different Monte Carlo algorithms. The first one is the importance sampling. Importance sampling is a Monte Carlo algorithm where can be used for approximated is a complex distribution that here is called SP with a simpler distribution Q, where we are able to sample from. So at first we are not able to sample from P, but we are able to do it from Q. That is called the importance density, because from Q we sample some independent particles and then we import them in P for approximating P. But due to the fact that we are using samples that comes from a different distribution, we have to fill the gap using some weights. So what we get are weighted particles. And here in the picture, we can see, for example, that the particles that are sampled from Q has different marker size, and the marker size is proportional to the weight of particle. So, for example, this particular particle has a high weight because it corresponds to a high probability region for P. Probability value, it's different. Okay. So we said that we get independent samples, so we can, for example, use the strong law of large numbers for approximating some integral values of P. And due to the fact that these samples are independent, we can parallelize the algorithm. So this is wonderful, but the main feature, that is the independence of sample, is also the main, the worst thing, because if we don't learn from the past, we cannot understand and we cannot store the region of a high probability of P. And that's why, for example, one can think about some different Monte Carlo algorithm that can be based on, for example, Markov chains, because Markov chains can store information from the past. So we introduce a famous Monte Carlo algorithm, Markov chain Monte Carlo algorithm, that is Metropolis Hastings, that is based on the construction of the Markov chain using an accept and reject scheme. So here we are interested in the construction of a chain. So what before was the importance density, now is the proposal density, because we want to use an accept and reject scheme. And this proposal density depends on the actual point. So we are in some point in the space, and then we choose a proposal density. And from this proposal density, we sample a proposal point in X tilde. This X tilde will be accept or reject in base of some probability alpha. So with probability alpha, we will accept the move, and with probability 1 minus alpha, we will reject the move. For example, now we reject this move, and then we get another proposal X tilde. In the case, for example, Q is symmetric, here we see that the probability alpha is nothing but the minimum between 1 and the ratio of P. This means that in this simpler case, if we are doing better, so if the proposal point belongs to a higher probability region instead of the previous one, then the accept is certain. So, for example, here in the picture, the accept is certain because the proposal Q is symmetric, and the proposed point belongs to a higher probability region. But if we are not in a higher point, then the reject is not certain. We reject with some probability. Okay, and once we have accepted the move, the proposal density changes, because here we see that the proposal density depends on the actual point. Well, so due to the fact that we are using Markov chains here, we can store informations from the past, but we cannot, for example, parallelize this algorithm because the samples are not independent. Okay, once we have introduced very quickly these two algorithms that are importance sampling and metropolis hustings, we can talk about the sequential Monte Carlo samplers. Here, the idea is to merge what we saw with importance sampling and metropolis hustings, applying sequentially these two algorithms to a sequence of distributions that can be imagined as a path between an easy distribution and a target distribution. So we would like to approximate a difficult distribution. Maybe something happened. No, okay. I'm only, okay, nothing. We want to approximate, sorry, complex density, and we can reach it by a smooth path between a known and easy density into the target one. So we at first consider this sequence of density, and we evolve at each time the particles using metropolis hustings. So we select some particles with a proposed scheme, with accept and reject scheme. Then we would like to evolve from the distribution at time t, so with samples at time t, into the distribution at time t+1. And this can be done using importance sampling. So using a terminology that comes from genetic, we can, for example, say that this is a sort of particle selection and density mutation. Okay. What is not clear from this brief and quickly introduction to sequential Monte Carlo samplers is that we are working in an increasing dimensional space that grows with the t, that can be seen also as time, and that this algorithm are useful for the approximation of complex densities and distribution, because if you think, for example, at importance sampling, is non-trivial to find a density that in high dimensional spaces where the proposed and the samples belongs to a non-null, non-negligible region for P. Then also there is another class of problems that can be solved using sequential Monte Carlo samplers, that are problems where the system evolves in time. Here, each density at any time can be seen as the density for the model for the system at time t, at fixed time. But here we have to talk something more about the distribution of the densities, because here we said that we start from a known density. We want to create a smooth path between the initial density and the target density, and we can link this with what we want to do, because we recall that we want to approximate the posterior distribution, and we can use the bias theorem. Using the bias theorem, we can link what's the posterior distribution with the product of the prior and the likelihood. And we can start from the prior, that is here written as Px, and going into the likelihood using a smooth path, giving more and more weight to the likelihood. We recall that in the MEG or EEG inverse problem, what we want to reconstruct are the number of dipoles, their locations, and their moments. So if also we get some data in a time interval, there are a lot of variables that at each time we need to evolve using sequential Monte Carlo samplers. So in 2040, Somariva and Sorrentino introduced one more prior assumption in the previous in the resolution of the problem, for the resolution of the problem, that allows a simplification of the problem. Okay, let's see here. We we are using an additive Gaussian noise, as we see in the previous presentation, and we are using here a uniform prior for the dipole location. So we are not preferring some places in the brain instead of one other, and we are using an Poisson Poisson distribution for number of dipoles. So in philosophy of Occam's razor, for example, here we prefer simpler configuration instead of complex one. The prior assumption that has been introduced is that the dipole moment has a normal distribution, a Gaussian distribution, with zero mean and some covariance matrix, with some diagonal covariance matrix that is proportional to the identity. With this assumption, we can simplify the problem, writing down the posterior distribution as the product of two terms. The first term can be written and can be analytically evaluated, while the second one can be analyzed with sequential Monte Carlo. So here we can reduce the complexity, the computational cost for getting the solution using sequential Monte Carlo. So the introduction of this prior assumption on the dipole moment introduced also a dependence on the standard deviation for the dipole moment, because here, if we are using, for example, if we're estimating a too big dipole moment standard deviation, we try to explain the data with bigger dipoles, with stronger dipoles. So we will use less dipoles than the true one. And on the other way, on the other hand, if we estimate it too small, we try to explain the data with more dipoles. Yes, sorry, I was wrong before. And what is more, that introduction, that prior on the dipole moment introduce a model inaccuracy due to the fact that the dipole moment does not have a Gaussian distribution. So the goal is to remove this limitation, but we don't really want to lose the benefits related with the conditionally linear Gaussian, with the sequential the semi-analytic Monte Carlo centers. So we want to make this parameter, that is the problem, a variable of our model. And this is equivalent to the introduction of an hyperprior into the model. With the introduction of this hyperprior, we can again simplify the problem using the conditionally linear Gaussian approximation, with the only difference that we have one more degree of freedom. We have one more variable in the problem. And we can at the same time simplify the problem where we said before that the Gaussian prior was inaccurate for our model. So with the introduction of the hyperprior, we can use a non-Gaussian prior at the same time we can use the semi-analytic approximation. So this is nothing but a generalization of the previous model. But here we said that we have introduced an hyperprior, but we have to fix it. And in order to fix this hyperprior, we have to underline what we really know or what we don't know about the parameter. We don't really know the order of magnitude of this parameter. So we want to give the same probability to different order of magnitude of our parameter, of the prior. So the most suitable one is the so-called log uniform or reciprocal distribution. This is called log uniform because the logarithm of the random variable that has this density is uniformly distributed in A. And so this is a suitable hyperprior for our model. Okay. And we see here something about multiple instance where we assume that recording made in different time intervals are independent by each other. So this means that the likelihood is nothing but the product of the likelihood made at each time. And with this assumption, as we said before, that sometimes we record in multiple time intervals, the posterior distribution is the product of the prior times the prior times the product of each likelihood at each time. This means also that I'm going fast, I know, but I have to say something more. So here we are saying that the located dipoles doesn't change their number and their locations in time, but they are allowed to change their dipole moments in time. So during the measurement, the point is always the same. It can change only the intensity of the active sources in the brain. Okay. Now we can relax and see some synthetic data, some numerical results. We used a total of 800 data, half for the EEG, half for MEG, where there are 100 data for each number of dipoles that goes from 1 to 4. And we choose random locations with only one constraint in the distance between two different dipoles in order to make the problem not too difficult, and in order to make the algorithm not confounding two dipoles with only one, because they are too close together. And then we choose a random dipole moment with a check in the intensity. So these are the data that have been generated. And for what concerned the numerical results, we compared the Sesame, that is the sequential Monte Carlo, with the conditionally linear Gaussian approximation, and the H-Sesame, that is the same algorithm with the introduction of the hyperprior. We choose 3 different orders of magnitude of the parameter, one order of magnitude less the true one, the order of magnitude of the true parameter, and 1 order of magnitude more. And we set 2 different metrics for the error. The first one is the error estimation on the number. So the number is of the estimated dipoles and the true one, the difference. And then the so-called optimal subpattern assignment metric, that is the OSPA. The OSPA error is the minimum distance between the estimated locations of dipoles and the all possible configurations of the true one. So we get the all possible configurations of the true one instead of the estimated one, and then we get the minimum distance. Looking at the numerical results, here we see 6 different confusion metrics, where in red we see the numerical results with Sesame, in blue we see the numerical results with H-Sesame, and as one can see here, we have extremely stable results with the introduction of the hyperprior, while we don't have this stability without the hyperprior. If we here by row we see the results having 1 less order of magnitude, the centered one is the order of magnitude, the right order of magnitude, and here we see 1 order of magnitude more. And the numerical result says that if we are wrong 1 less order of magnitude, we get more dipoles than the true one, because we are trying to explain the data with smaller dipoles. Then if we are trying to explain the data with bigger dipoles, so dipoles that have a stronger intensity, we are trying to explain the data with less dipoles, as we said in the introduction, where we saw why do we need an hyperprior. While with the hyperprior, we see extremely stable results. The same is with the OSPA error. I'm out of time, so we can skip on this, but also here we see a strong, an extremely stability for the H-Sesame that doesn't belong to the normal Sesame. So In conclusion, we saw the Bayesian resolution for the MEG inverse problem, and especially the resolution with a conditional linear Gaussian approach. And here we saw that there was a problem, extremely dependent on one parameter of the input, and we resolved it by the introduction of a hyperprior for overcoming these limitations. And then we saw also that these results has a numerical support. And so thank you for the attention.
Thanks a lot, Ale. It was very clear. Thanks.
Welcome.
So, is there some question?
Giusto, devo unmutare. Sorry, I have to unmute everyone. Okay, so.
In the middle time, I ask you something. Okay, what is some future? Okay, there is a Sarah. Is unmuted? Okay.
Yeah, I can speak. At the beginning of your slides, you say that this approach can be applied for EEG and MEG. Have you thought about applying it for the combination of the two? And do you have an idea about to do it, or have you already done it?
No, but the combination. Okay, yeah, no.
So to use at the same time both the data EEG and MEG.
No,
Okay.
I've not done it yet, and maybe I'll do it in the future, but I don't know when now.
Okay.
And did you use for EEG data or only MEG?
But the results that I've showed you in the slide are only by MEG, okay. But I explained I didn't put the EEG data for the EEG results for time questions.
Okay, but I guess the results are more or less.
Okay, no, maybe I understood not well the question of Sarah, because I had the two results, but one for the EEG, one for MEG, but not together in a single
experiment.
Yeah, in a single experiment.
So is it in the plan for the future?
Yeah.
Okay. We see.
Yeah, thank you. You answered my question.
Other questions? Okay. Seems no more questions.